So we've been here in chapter 2. Remember, chapter 1 was all about collecting data, and in chapter 2, we're all about describing the data. Okay, we're going to describe the data graphically and numerically. And the type of graphs and summary statistics that we're going to use are going to be dependent on the number and type of variables that we have. So in section 2.1, that's where we talked about what to do when we had one categorical variable. We talked about what to do when you had two categorical variables. And now we're looking at one quantitative variable. And one quantitative variables in general are a little bit more complex than categorical variables. So we have a few more things. So section 2.2 and 2.3, and even a little bit of 2.4 are all about one quantitative variable. I actually want to do a couple little review problems here to get us back up to speed, and then we're going to talk about measures of spread. So this here is some data that I took from, I actually took it from last semester's first day survey because the distance from campus, I don't know how you say how far you are from campus when you're attending classes online. So I don't know if people were just choosing like the campus that they normally go to or what. It was kind of a dumb question to leave on there for you guys since your commute is probably like 5 feet, you know, from your bed to your desk in your bedroom, or maybe all the way to your kitchen table like I'm sitting at. So anyway, this is from last semester. These are 9 students' responses for how far did they live from campus. Okay, so the first thing I'm going to do here is we're going to draw a dot plot. Remember, dot plots are super easy to draw by hand because all we have to do is draw the x-axis, and then we're going to put a dot, or the way that I have to do it on my computer is draw an X, because it does not like it when I try to draw dots. It thinks I'm trying to do something else. But an X is fine. We've done stars before in our class, you know, so any old little symbol you like. But basically when we're drawing our X-axis, it's a number line. So in my case here, you know, my number line, I can see my smallest thing is 3 and my largest thing is 35. So I think I'm going to count by 5s on my number line down here. So I'm going to have, let's see, 0, 5, 10, 15, 20, 25, 30, 35, 40. All right, and then I'm just going to put an X for each value. So I have 9, so 9's around here. So I'm going to put an X or a dot. This was a 5, by the way. It kind of looks like a 3. Now I made it to look like a 5. Whoops. Okay, and then I have 15, so that's here. 35, here. 6, so 6 is about right here. 5, 7, so I've kind of got a bunch all squished together here. 2 3s, so that's going to be 3, 3, and then 6, so that one was here. All right, so this is kind of a little squanchy little dot plot here, but we can get a general idea of the shape of this distribution even from this little dot plot here. So what kind of shape do you think this distribution has? So this one's going to be right skewed. So you can kind of see that there's a whole bunch of points kind of clustered together down here, and then there's a long tail over here. We definitely have something that looks like an outlier out here. The person lives 35 miles from campus. And we have a bunch of points that are clustered down on here on this end. So the skewness goes with the tail. So this one, the tail is on the right side. So it's going to be right skewed. Okay, so next we want to find the mean. Okay, what is the symbol for the sample mean? So when I'm looking for the mean of a sample, which in this case, this is not all the students at ACC. So obviously this is just a sample. So yeah, the notation or the symbol for the sample mean is X bar. Okay, to find X bar, we're going to add up all the X values and divide by the total number of X values. Okay, so when I added them all up, then I got 89. 89 goes in my numerator, divided by 9, gives me a mean of 9.88888. So 9.89. So this is my mean. Okay, next I want to figure out my median. And one thing, just make sure that you use, whenever you're rounding in our class, 95% of the time we're going to use standard rounding rules. There's like 2 exceptions to using the standard rounding rules, and I'll tell you what those are when we get those there, but those are like way later in the semester, and they're very specific cases. So in general, make sure you're using standard rounding rules when you're, if you're rounding here. Okay, so to figure out the median, the first thing we do is we're going to order the observations from smallest to largest. So up here, looking at my numbers, I've got 3, 3, 5, 2 6s, a 7, 9, 15, and 35. Let me see if I got them all. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I did. Okay, so now I'm going to work my way into the center. And 9 is an odd number. So when I get to the center, there's just going to be one number, and that one number is going to be my median. So I've got 3 and 35, 3 and 15, 5 and 9, 6 and 7, and 6. So 6, this number right here in the center, is going to be my median. So my median is 6, and my mean is 9.89. In this case, they're pretty different from each other. So which one is going to be a better measure of center for this data, the mean or the median? Should we go with 6 or should we go with the almost 10? The median, right? Because the median is resistant. Okay, so today we're talking about measures of spread. Okay, remember, spread is how spread out is the data, how much variation is there in the data set. And we have 2 measures of spread that we're going to look at. And the first one that we're going to look at is called the 5-number summary. And pretty much just like the name implies, then the 5-number summary has 5 numbers in it. So the 5 numbers that are part of the 5-number summary are, first of all, the minimum, okay, which is just going to be the smallest number in the data set. Then we're going to have what we call Q1, which is also called the first quartile. And we'll talk about that, what that is in a second. Okay, the next number is the median, and we've already learned what the median is. See if I can spell it right. Okay, so the median is that middle value of the data set. Next, we have Q3, which is the third quartile. And then finally, we have the maximum, which is just going to be the largest number in the data set. So these are the 5 numbers that make up the 5-number summary. And basically what the 5-number summary does is it splits the data into 4 quarters, or 4 equal parts. So it splits the data into 4 equal parts. Okay, so basically we're essentially lining up all the observations from smallest to largest, and then we're putting an equal number of observations in 4 different groups is what we're doing here. So we're dividing it into 4s with 25% of the data in each of those groups. So here's kind of a picture of what that looks like. Okay, so between the minimum and Q1, we have 25% of the data. Between Q1 and the median, then we have another 25% of the data. Between the median and Q3, then we have another 25% of the data. And between Q3 and the maximum, then we have another 25% of the data. So this Q1 and this Q3, we call those the first quartile and the third quartile. And basically, when we're finding those values, what we're doing is it's similar to, let's say we had a candy bar, okay, chocolate candy bar. We're gonna make it dark chocolate. It's gonna be a Milky Way Midnight because that's my favorite candy bar. And if I had a dark chocolate Milky Way Midnight candy bar sitting right here, and I picked 3 of you that I was gonna share my candy bar with, then the fairest way for me to split this up would be to first cut the candy bar in half, and then I would cut each half in half again, right? And that's basically exactly what we're gonna do with our data set. So the first thing we're gonna do is we're gonna cut the data in half, and we do that by finding the median. So then we're going to split the observations at the median. Okay, and then we're going to find the median of the lower half of the data. That's going to be our Q1. So Q1 is the median of the lower half of the data. And then Q3 is going to be the median of the upper half of the data. So the top 50% of the data, we're going to take that, we're going to find the median of those values, and that's going to be our Q3. So Q3 is the median of the upper half of the data. All right, so we're going to look at how to do that in a data set here. But first, just kind of looking at what this 5-number summary does, it tells us, so if I look at Q1, okay, this, as you can see by the groupings here, 25% of the data is less than Q1. Okay, you can see that 50% of the data is less than the median. Okay, 75% of the data is less than Q3, and then of course 100% of the data is less than the maximum. When we talk about the percent of the data that is less than a value, another term for that is a percentile. So a percentile, and write this down even though it's not on a write it down slide, still write it down. The pth percentile is the value in which is greater than p% of the data. So that means if I'm in the 72nd percentile, then I did better than 72% of the people. Or in other words, 72% of the people are lower than me. So when we talk about the quartiles, we often refer to them as the percentiles as well, because Q1 is also the 25th percentile. Okay, the median is also the 50th percentile, and Q3 is also the 75th percentile. So here's kind of picture what that looks like. You can see, okay, Q1 is also the 25th percentile, median is the 50th percentile, Q3 is the 75th percentile. So, and you should kind of be familiar with the term percentile. Anytime you've taken one of those standardized tests like ACT or SAT or one of those, then you're going to get your percentile score. They're going to tell you where you fell with everybody else. It's kind of a little bit more of a standardized way to compare yourself to other people a little bit, is by looking at your percentile. Also, if your parents have been taking you in for your well child visits since you were a baby, then every time they go in, they say, oh, here's your height. It looks like you're in the 15th percentile or something like that. So you've probably heard that term percentile before. Okay, so back to the data set that we first looked at with the number of miles we live from campus. We're going to go ahead and see if we can find the 5-number summary for that one. First thing I did was put it in order from smallest to largest. So here it was originally, here it is now that we've made it smallest to largest. So first thing I want to do is I want to find the median. So there's 9 observations. So when I work my way in from both sides, okay, then I find out that 6 is my median. So this is the median. All right, so I'm going to put down 6 for my median. And while I'm here, I can fill in the min and the max because those are the easy ones. Okay, the minimum is 3 and the maximum is 35. So minimum, just the smallest number, maximum, the biggest number. So now all I have to do is figure out those quartiles, okay? So I'm gonna cut my data in half. The key to this is I want exactly half, okay? So like, let's say that I have a pile of Skittles. Let's say I have 9 Skittles and I have 2 kids, then I'm gonna split the Skittles between. And if you have kids or you've been around kids or you've been a kid yourself, then you know that they have to give the same amount or there's going to be crying and tears involved. So I can't give, there's 9 Skittles. I can't give one kid 5 Skittles and the other kid 4 Skittles because then there will be upheaval and uproar. So it has to be exact. If I had 10 Skittles, everything would be great. I could just give one kid 5, the other kid 5. Everybody goes home happy. So if I have an even number of observations, I just split the data exactly in half. Half goes with one side, half goes with the other side. The only problem we sometimes get is when we have this odd number here and I have a middle Skittle. Okay, so if I had these 2 kids and I said 1 for you, 1 for you, 1 for you, 1 for you. Now each kid has 4 Skittles and I'm holding 1 Skittle in my hand. What do I do with that one Skittle? Any guesses? Okay, well, I can tell you that it's pretty much impossible to cut a Skittle in half because we have actually tried that at our house. So you can't cut the Skittle in half. That's not going to work. Ah, yes, I see it there. Oh, make them dual. I like that one. Okay, and I see a couple of people, you're going to eat it. You are going to eat it, right? Because you're not going to give it to one of the kids because they're going to fight about it. So you just eat the Skittle. Everybody's happy. So that's basically what we're going to do here. Okay, so if there's a Skittle left in the middle or an observation left in the middle, like there is in this case, you eat it. It doesn't go with either side. Okay, and then that way we can have exactly 4 observations on one side and 4 observations, or the same number of observations on each side. In this case, it's 4 and 4, but anytime you have an odd number, the middleman just sits out, that's the Skittle you eat, and then the other observations go on either side. Okay, so once you've divided the data in half, that's the hard part about finding the quartiles, then I just have to find the median of each half. So here with these lower 4 observations, even numbers, so when I get to the middle, I have to take the average of 3 and 5. So my Q1 is going to be 4. On the upper half of things here, I'm going to have to take the average of 9 and 15, which, yeah, I know I should be able to do this in my head, but just in case, I'm going to do it on my calculator so I don't screw it up. Okay, and I'm going to get 12. So Q3 is 12. Okay, so Q1 is 4 and Q3 is 12. And this is my 5-number summary. Remember, 5-number summary is a measure of spread. So how is this kind of measuring our spread? Well, first of all, I can see what we call the range. Okay, the range is the maximum minus the minimum. So you can see I had a span of 32 values, 32 miles. The closest one to campus was 3 miles. The farthest one was 35. So that's a span of 32. So that's kind of interesting. Also, remember, in between each of these is 25% of the data. So I can see here, looking at these numbers, okay, that you remember the Q3 is that 75th percentile. I can see that 75% of the students live, within 12 miles of campus, and only a few people live way far away, between 12 and 35 miles away from campus. Because there's such a big gap between Q3 and the maximum, that is kind of an indication to me that this data is skewed. And also that the minimum and Q1 are so close together there. All these things are pretty close, and then it starts getting farther and then really far away. Just by looking at the 5-number summary, you can kind of identify that we have a skewed distribution here. And we could see it happen the opposite way, where the minimum is way out there, and then the other values are close in, which would tell us it's less skewed. So that's one way that we look at the spread of the data using the 5-number summary. Thinking about the 5-number summary, how we're going to kind of make sense of that for now. So I'm going to call this making sense of the 5-number summary. Okay, first thing is we can sort of tell whether the data is symmetric or skewed based on the numbers in the 5-number summary. So we can tell, I'll put that down. So we can tell a little bit about the shape, like symmetric versus skewed, by looking at the numbers in the 5-number summary. So we can tell a little bit about the shape of the data, symmetric versus skewed, from the numbers in the 5-number summary. Okay, the next thing that we can look at is what we call the range. Okay, and the range is just the maximum minus the minimum value. So again, this is going to tell us a little bit like how spread out are those data points. It tells us, like I said, when we were looking at the miles from campus, it said, hey, there was a range of 32 miles from the smallest number to the biggest number. So it's, again, measuring spread there. Okay, the third thing that we can measure with our 5-number summary is something called the IQR, which stands for the interquartile range. So interquartile range. And we find the interquartile range, the IQR, by taking Q3 minus Q1. So this tells us basically the range of the middle 50% of the data, because between Q3 and Q1 is 50% of the data. Here is a data set. Based on these numbers, what do you think the shape of this data is? Symmetric, right skewed, left skewed, or impossible to tell? Okay, good. So this one's going to be right skewed. We can tell that because the maximum is like way far away from all these other values. So the maximum, the high number, means there's going to be an outlier over there on the right, like if you're looking at this on a number line, which is going to make it right skewed. So this is what it looks like when we actually look at it. So the range is the max minus min, the IQR is Q3 minus Q1. Thinking about the range, is the range resistant? So is it resistant to outliers? Do you think yes or no? Okay, good. So no, the range is not going to be resistant because remember, if you have outliers, those are going to be the big numbers that are way out there. So, so the max and the min are going to be the outliers if we have any. So it's definitely going to be affected by outliers. And if we have an outlier, it's going to make our range seem, like the spread seem like it's really huge. So the range is, so the range is not resistant. So the answer is no. But what about the IQR? Is the IQR resistant? So remember, to find the IQR, we just take Q3 minus Q1. Yeah, so the IQR, because we're talking about that middle 50% of the data, that one is going to be resistant to outliers. So the IQR is a resistant measure of spread. So that's why we even have the IQR, why we kind of look at that, is because it's going to be more resistant than the range. And in section 2.4, we're going to talk even more about the 5-number summary and about some other cool things that we can do with it. Okay, so let's talk about our second measure of spread, which is going to be the standard deviation. Okay, and the standard deviation is going to be the average distance each point is from the mean. So standard deviation is the average distance. So average distance, that says distance, each point is from the mean. Okay, so if you have a big number for standard deviation, that means that the points are more spread out. And if you have a small number for standard deviation, that means that the points are less spread out. So big number, big standard deviation means points are more spread out. Okay, and similarly, a small number means that the points are less spread out. All right, when we're talking about notation, okay, for the sample standard deviation, we're going to call that S. And for our population standard deviation, we're going to use the Greek letter sigma, which kind of looks like an O that's wearing a little baseball cap, maybe. Looks a little bit like that, or like an O with like a little curly Q or tail kind of on the top. So that's what we're going to use for the population. So our formula that we're going to use for standard deviation, I'm gonna show you what it looks like. You don't actually have to use the formula in our class. We're just going to have software compute the standard deviation for us. But sometimes it can be helpful to look at the formula to kind of understand what it's doing. So standard deviation is the square root, the sum of each observation minus the mean squared divided by n minus 1. When we're looking at x minus x bar, that's the distance from that point to the mean. So like the distance like on a number line is what we're looking at here. We're just saying, hey, how far away or what is the distance from that point to the mean? And then, if we're talking about an average here, so you think add them all up, divide by the total, but that doesn't work because if you do that, you actually end up getting 0 because we have part of the points above the mean, part of the points below the mean. So we got these negative numbers and positive numbers. So that's why you have to do all these kooky things by squaring, then adding them up, then dividing, and then taking the square root to get back to regular numbers. So like I said, you're not going to have to use this formula. What you really need to know is bigger standard deviation means that the points are more spread out. Smaller standard deviation means that the points are less spread out. And we're going to talk about a couple other things here that are helpful for understanding standard deviation or using standard deviation to help us with understanding the data a little bit better. Okay, so here's kind of just an example here. You can see that standard deviation up here is 1. You can see everything's really tightly clustered together. Down here, the standard deviation is 4, so the points are a lot more spread out. Let's talk about a few things that we can do, or that the standard deviation is going to be helpful for. So I call this making sense of the standard deviation. Okay, so making sense of the standard deviation. The first thing we're going to talk about is something called the 95% rule. Okay, and the 95% rule says that if our data is bell-shaped symmetric, then about 95% of the observations are going to be within 2 standard deviations of the mean. So we'll write that down, and then we're going to talk more about what that means. So what it says is, if the shape of the distribution is bell-shaped symmetric, then about 95% of the observations will be within 2 standard deviations of the mean. Okay, so in other words, 95% of the data, if we're talking about a population, would be between mu minus 2 sigma and mu plus 2 sigma. So in other words, in a population, 95% of the data would be within mu minus 2 sigma and mu plus 2 times sigma. Okay, so for example, let's say that you guys take the first test and I come back and tell you, hey guys, guess what? On our first exam, the mean score, mu, was equal to 85 and the standard deviation was equal to 5. Okay, and I tell you, hey, it turns out also that the data was bell-shaped symmetric. So you know the data is bell-shaped symmetric, you know the mean and the standard deviation. If I take mu minus 2 times sigma, that would be 85 minus 2 times 5. That gives me, so 2 times 5 is 10, so that's going to give me 75. Okay, now I'm going to do the same thing here, but now I'm going to do mu plus 2 sigma. So mu plus 2 sigma is going to give me 85 plus 2 times 5. Okay, so again, 2 times 5 is 10, so 85 plus 10 is 95. So what this tells me, according to the 95% rule, is that 95% of the class scored between 75 and 95 on this exam. Okay, so the 95% rule just says, hey, here's where 95% of the values were. And we just get those numbers that they're between by just adding and subtracting 2 times the value of the standard deviation from the mean. Here's an example. Based on student survey data, pulse rates for a sample of college students are approximately bell-shaped. They have a mean of 69.6 and a standard deviation of 12.2. Okay, so what interval is likely to contain 95% of the pulse rates in this sample? So this is just what we were just looking at. Okay, now I've given you a mean 69.6 and a standard deviation of 12.2, and I want to know, okay, between what 2 values are 95% of the pulse rates? Okay, so to figure that out, we take the mean minus 2 standard deviations and the mean plus 2 standard deviations, and we see what 2 numbers we get. So I'll give you a minute just to see if you can figure out the mean minus 2 standard deviations and the mean plus 2 standard deviations. So just what we did with the test scores, only now you're going to do it with the pulse rate values. Okay, good. Looks like everybody's getting about the same answer over there. And you get the same thing that I got too. So if you take that 69.6, we're going to add and subtract 2 times that 12.2. When I subtract, I get 45.2, and then when I add, I get 94. So that tells me that 95% of students had pulse rates between 45.2 and 94 beats per minute. All right, I'm gonna back this up and show you this picture here. This says, okay, remember we said that the distribution had to be bell-shaped symmetric, so this is kind of a smoothed out histogram would look like this lovely little bell shape here. Okay, and again, we're saying that 95% of the values are going to be between the mean minus 2 times the standard deviation and the mean plus 2 times the standard deviation. Now, we've already seen that if you have the mean and the standard deviation, we can compute an interval to where 95% of the values are going to be in that interval. We can also use this rule kind of in reverse to help give us an estimate of the standard deviation if we have, say, a histogram or a dot plot and we don't have the standard deviation given to us. So if we're just looking at a histogram and we're trying to estimate standard deviation, we can use this 95% rule kind of backwards. So this is how we are going to do that. Okay, so first of all, if we look here, you can see that 95% is a lot of our curve, but it's not the whole thing. Okay, so if I look at where we make the cutoff for 95 here, okay, there's still a little bit left on either side. Okay, the other thing that we can tell from my picture here is that if I look between this lower number here and this higher number here, okay, the distance from one to the other is going to be 4 of these standard deviation hops. So the distance from here to here is 1 standard deviation. From here to here, it's another standard deviation. From here to here, it's another standard deviation. From here to here, it's another standard deviation. So basically, if I took this lower number right here and I added 4 times the standard deviation, then I would get this higher number here. Okay, so does that make sense so far? All right, so now let's talk about how I can use this rule with a histogram to help me estimate standard deviation. Well, my histogram is going to be bell-shaped symmetric-ish. Okay, first thing I'm going to do is I'm going to cut off a little bit on either side. That's this part and this part. Remember, we have to come in just a little bit so that we get to the 95. We're cutting off 2.5% on either side. So it's not very much. We're just cutting off a little bit. Okay, so you're going to take your histogram, you're going to be at the ends, you're going to come in a little bit and draw some vertical lines. Okay, so I draw my vertical line here and I draw my vertical line here. Okay, I look at where those lines cross the x-axis. I'm going to have a big number and a little number. So to estimate S, okay, what I'm going to do is I'm going to take the big number, subtract the little number, and I'm going to divide by 4. Okay, why am I dividing by 4? Because the distance from the little number to the big number is 4 of these S's. It's 4 standard deviations. So I'm going to divide by 4. Okay, and this is the formula all the time to do this estimate for the standard deviation. So I come in a little bit, I'm just chopping off the little teeny ends of my histogram. I look at the big number, I subtract the little number from where I'm at, and I divide by 4. And I'm always going to divide by 4 because using this rule, that's how many standard deviations there are. Okay, so let's look at an example to see how this is going to actually work. Okay, but make sure you've written down on your paper that to estimate S, you take the big number. Well, first of all, you cut off a little bit on either side, then take the big number minus the little number and divide by 4. Okay, so we looked at that already. Okay, so let's look at this one here, this top one here. Okay, so again, first I'm going to cut off a little bit on either side. So here's my histogram. It's bell-shaped symmetric. It's lovely. Okay, I'm cutting off 2.5%. So looking at my picture here, you can kind of see how big 2.5% is relative to the whole. So it's not eensy-weensy, but it's not really that big either. So I want to cut off a little bit. So here on this one, I think I would make my cut about right here and right here. Okay, so I've cut off about 2.5%, just a little bit on either side. Okay, then I look where I made my cut. I made my cut at +2 and -2. So now I'm going to take the big number, which is that +2. I'm going to subtract my little number, which is that -2, and I divide by 4. Remember, we always divide by 4. The big number and little number will change depending on your histogram, but the 4 in the denominator is going to stay the same. So 2 minus -2 is actually a positive, makes that positive, so I end up with 4 over 4. which gives me an estimate of the standard deviation. I'm not of S. Gives me 1. I get 1 for my estimate for standard deviation. Okay, now see if you can look at this bottom histogram here and see if you can do the same thing. So you see if you can eyeball it, see where you would cut off a little bit, like not too little, not too much. It's kind of a fine line there, but we're cutting off a little bit on either side and then taking the big number minus the little number divided by 4. All right, so far everybody that's put their answer over in the chat window, looks like what they did was they cut off at -10 and +10, and then they took 10 minus -10 over 4 and got 5 for our estimate of standard deviation. When I did it, I came in just a little bit more because that looked like so weensy. It didn't look quite like 2.5% to me. So I actually made my cut right here at about 8 is what I called it. So I made it at -8 and +8. So I took 8 minus -8 divided by 4. So I ended up with an estimate of about 4. If I was having you do this on an exam, then I would have accepted both of these answers. Because again, we are just kind of approximating here. We're estimating. If you would have gone from like -15 to +15, I wouldn't take that. Okay, I'm going to make sure that you're cutting off a little bit and not cutting off like a ginormous amount. Because remember, we're looking at 2.5% here. So I'm looking for like a reasonable place where you made your cut. So if we actually looked at the actual standard deviation of this data, it actually was 1 for that top histogram, and for the bottom one, it is 4. So mine was a little bit closer than some of y'all's, but like I said, I would have accepted the one that you guys did if this was an exam. Okay, so here's another chance for you to try some out here. So see if you can estimate the standard deviation for hours of sleep per night on this histogram. And here I've even given you some options to choose from for the standard deviation. All right, I'm seeing a lot of C's, and that is the correct answer. So on this one, again, we're going to cut off just a little bit. This one kind of makes it easy because there's just a little bit in that one little bar, so we can just cut off 1 bar on each side. So when we do that, then our big number is 10, and our little number is 2. We're always going to divide by 4, so I end up with 8 over 4, which is 2. So pretty good guess. And it's actually amazing, like if you look at real data, this does a pretty good job of estimating the standard deviation. You get a number that's pretty close to the real standard deviation, which is kind of cool if you've ever tried to calculate standard deviation by hand. It's a real pain in the tushy. So this is a nice way to approximate it without having to go to all that extra work. Okay, so that's one way that we're going to use the standard deviation to kind of help us make sense of the data, help us make sense of the spread, or going to help us to be able to, at least that's going to help us like figure out kind of where is 95% of the data, and then also we have now this tool to help us estimate standard deviation. So another way that we're going to make sense of the standard deviation is by looking at a Z-score. So still under the heading of making sense of standard deviation, number 1 was the 95% rule. Now we're looking at number 2, which is something called a Z-score. Okay, and what a Z-score is it is something that kind of puts measurements on the same scale, so to speak. So it puts measurements on the same scale, so to speak. So what it's going to do is it's going to change the measurement so that instead of we're measuring in inches or you know, whatever time or whatever our variable was measured in, we're going to be measuring in number of standard deviations away from the mean. So the Z-score tells us how many standard deviations our point is from the mean. So it tells us how many standard deviations our point is from the mean. All right, so obviously the bigger or the farther away from 0 your number is, the more extreme your value is, the further it is from the mean. And a positive or negative Z-score just tells you if your value is above or below the mean. So if you have a positive Z-score, then your value is above the mean, and a negative Z-score means that your value is below the mean. When we have Z-scores that are less than -2 or more than +2, we call those extreme points. They're extreme observations. So values of Z-score that are less than -2 or greater than +2 indicate an extreme value. And if you think about our 95% rule, we said if you're 2 standard deviations away from the mean, which is what a Z-score of 2 would mean, we said 95% of the values are going to be within 2 standard deviations of the mean. So less than 5% of the time, if you have a bell-shaped symmetric distribution, are you going to get Z-scores that are less than 2 or greater than +2. So this is how we're going to calculate the Z-score for population values. It's a similar process for both, but the symbols are different. Okay, so if you have a population value, then Z is going to be equal to X minus mu divided by sigma. Okay, so we're just taking whatever X value we're interested in, we're subtracting the mean, and we're dividing by the standard deviation. And for samples, then same process, only we're going to use different notation for the sample mean and the sample standard deviation. So we're going to have X minus X bar over S. So positive Z-score meant that our value was above the mean, and a negative Z-score meant the value was below the mean. Okay, so to find the Z-score, we're just taking our value, we're subtracting the mean, we're dividing by the standard deviation. Same thing for samples, subtracting the mean, dividing by the standard deviation. All right, so here's the example we're going to look at. We have these 2 scores of tests that you often take to get into college. Probably a bunch of you have taken one or the other, or even both of these tests, the ACT or the SAT, but they're measured on different scales. So let's say you take the ACT and you take the SAT, and you're wondering which one did you do better on. Your ACT score is 28, and your ACT score is 28, and your combined SAT score is 2100. But just looking at those numbers, it's hard to tell, oh yeah, I did better on, you really can't tell which one you did better on. So one way we can put both of these on the same scale so that we can compare them would be finding the Z-score. So we would want to find the Z-score for the ACT, and then separately find the Z-score for the SAT, and then we can compare the Z-scores to see which one is the furthest above the mean. So starting with the ACT, okay, so for the ACT, my Z-score for that one, okay, remember we're going to take X minus mu divided by sigma. Okay, they're always going to give you the mu and the sigma, or the X bar and the S in the problem, and the X value is going to be the thing that's kind of mentioned in the problem statement, like it's the value under question. So in this case, it's going to be 28. So to find the Z-score for the ACT, I would take 28 minus the mean, which was 21, divided by standard deviation, which was 5. So I have 28 minus 21, which is 7. 7 divided by 5 gives me 1.4. Okay, so for the ACT, I get a Z-score of 1.4. And now I want to do the same thing with my SAT score. Okay, so for my Z-score for the SAT, I'm going to take X minus mu over sigma. Again, this time the X I'm interested in is that 2100. So I'm going to take 2100 minus the mean for that SAT, which was 1500, divided by the standard deviation, which is 325. So I take 2100 minus 1500, which gives me 600, and then I take 600 divided by 325, and I get 1.85 by round. Okay, so ACT, my Z-score was 1.4, SAT, my Z-score was 1.85. So which one of those did I actually do better on, the ACT or the SAT, based on my Z-score? I did better on the SAT because it had a higher Z-score, meaning it was further away from the mean. And somebody asked if there's like a unit on the Z-score. There's not really a unit other than it's the number of standard deviations that point is from the mean. So the Z-score, that's kind of one of the reasons why we compute a Z-score, is it kind of gets rid of our units that we measured in, and now it's all about number of standard deviations away from the mean. So the SAT Z-score of 1.85 says my SAT score was 1.85 standard deviations above average. And the ACT Z-score says I was 1.4 standard deviations above average. And was either one of these an unusual observation? No, okay, because it wasn't greater than 2 or less than -2. The SAT one's getting close, but it wasn't quite there yet.